Hi everybody, apologies for the delays. So it's nice to have you here, and I'd like to thank John for inviting me here to give you a talk. I like this talk to be interactive. I don't know what's your background, so please ask questions at any time if something is unclear, especially early on. So this talk will be about DOT, the dependent object types calculus, which is the core type system of the Scala programming language. So DOT has been studied for theoretical reasons. So the first question, I think, is why should a programmer, not a theoretician, understand DOT? And I'm not sure it's for everybody, but this DOT is the foundation of the Scala type system. So it is much smaller than the full Scala. It helps build intuition for how the Scala type system works. Can we turn this off? There's some echo for staying here. Let's see. DOT helps build intuition for the full Scala type system, and it's much smaller and fully specified. So that's the advantage of having a core language which is formalized and which has been studied and encoded in proof assistance. So in some, DOT gives you a simple way, smaller way, something smaller to understand as a way to also understand full Scala. So as a bit of background, why was DOT invented? It was invented to specify the core type system for Scala 3. And, sorry, wait a second. I still hear some echo. Is there something we can do about this? Because I see people in the audience cringing, not just myself. Is there?
I don't know if the technicians are still here.
So, okay. Still, okay, it sounds like it's better. Do you still hear me? Still being recorded? Good. Thank you very much. Okay. So the goal of DOT was invented to specify the core type system for Scala 3. And not only specify it, but specify it in a formal way, because specifying a type system in English is a dangerous enterprise. And the other goal was to validate its correctness formally. So what is DOT? DOT is a small type system. It's a small programming language with a type system. It is small but very expressive. It is mostly a Scala subset in which other features can be encoded. It is, in a sense, simple in the sense that it's simpler than full Scala. It has still lots of the interesting and complicated features of the language, because the goal is to not understand just a toy, but to understand Scala. The other thing is, I haven't said what are the guarantees that we have for DOT. The guarantee that we have, the prime guarantee, is type soundness. So if a program is accepted by the type checker as well typed, then it will not go wrong. It will not have a type error at runtime. And this has been shown by mechanized proofs, that is, proofs that have been written down formally and explained and checked by computers. This is the guarantee that we have today. What we might hope to get in the future are other guarantees like decidable type checking and quite possibly parametricity. We're not there yet, but hope to get there someday. This has been the quest for a core, for a sound core for the Scala type system has been going on for a long time. And these are the names of some of the people who have been involved. I will not with the full slides, and they're not in a particular order, but I'll give you some credit. So I am speaking here about this because I'm a Scala programmer and an academic, and I've been working myself on doing research on DOT, some collaborators. I will not present this research here. I will keep this talk pretty informal. Just to give an introduction. Few caveats. There are different variants of dot around in the literature, and this is a combination that I pick for didactic purposes, and I will not go into the proofs. So, in the rest of this talk, what I want to present is examples of dot program shown in Scala syntax, so that we can go from our understanding of Scala to understanding of dot. And then we will see the encoding of some other Scala features in this small subset, and then we will see what actually dot is, what is the actual syntax of dot programs, and what is the dot type system. So let's start by taking a look at a few examples. First, let's understand what is that we have in dot. Dot is the extremely small language, and we only have core features for functional programming and object-oriented programming. So what we can write in programs are first-class functions for the functional side, and objects which will have both value members and type members. We do not have classes, trait, inheritance, anything like that. We express everything using objects. And now to get this a bit more concrete, let's look at this example. So here, we have an example of a trait sec module which specifies a small interface, a very small subset of the interface of a sequence library. So an object implementing this interface will have two type members which specify the type of elements and the type of the sequence. In this interface, these types are left abstract. So we don't know how they are defined. And the interface also specifies that we have methods for operating on these collections, for creating collections, for doing tests on them. We would need to have many more methods, but we keep the examples here very small to make them fit on the slides. Now, we can also define implementations of this interface, and to do that, we go implementing objects that fulfill this interface and that specify how the abstract types are defined. So here, for instance, we can implement this interface using simply list. What is important here is that in this method list stack creates for each type a module implementing this interface and leaves the type of sequence abstract. So from outside, we do not know what sequence is implementing, how this type is defined. We can write code that uses an implementation of this sequence to operate on sequence. And here, what we will see is that, so this is a method using this interface, and it takes an implementation of the seq module, and it uses path-dependent types. So it will take sequences of the type specified by seq module. Wait, what? Sorry, screensaver. We still. Now, one question for you. How many of you are already familiar with abstract types? Yes. Very well. Looks like almost everybody. So there's some. Is there anybody who has questions here? Looks like not. Great. So I ask this because the core feature that we will see in dot is support for abstract types. That's a core thing that is being modeled because it's a core source of questions. It was a core source of questions about type soundness for Scala 2. So the other thing that we need to see in this example is just to reinforce the point that the type of sequences is abstract. So from outside of if we create an implementation of this sequence and we try to use it, I said that values have object and type members. So objects have value and type members. So here, this type, what it will correspond to is, in fact, a list of int. However, to preserve abstraction, because this is what in secmod.sig is hidden, is an implementation detail, we do not allow converting this list of int to such a sequence. Okay? So this is, it should be known. So this is the important feature, the crucial feature of abstract types, which we use for encapsulation. This is one of the core things that we model in Dot. So this example now that I've shown is some Scala code, but it is not yet Dot. It's almost Dot. So let's go back to this code and show how it changes to bring it closer to Dot itself. We don't have traits, as I said. So what we have are structural types. So instead of defining sig module as a trait, we define it as a type which is equal to this body. The body is in fact the same, basically. And we do not have inheritance. So to implement this trait, we're going to write a method which creates a new object and which defines everything from scratch. So if we had something that we inherited from a superclass or from a trait, in Dot we would have to copy the implementation we used to inherit, because Dot does not model inheritance. That's a separate concern. Then the idea is, if you want to deal with inheritance, you can take your Scala program, desugar the inheritance by hand or automatically, and obtain a program in Dot that you can study. So this is why Dot is still useful to understand full Scala with inheritance. Now, the other thing which changes that instead of having refinement types, we just use intersection types. So this is the ampersand here. That's the Scala 3 syntax for intersections. And unlike the Scala 2 intersection now we're using with, this is symmetric. So we see the intersection of sig module and this type is just a type. Intersection is just a type which contains members in both types. Yes, there is a question?
Could you explain also refinement types?
I mean, I would say in refinement types in Scala, at least in this example, are just convenient syntax that we have, that we use here for expressing something like the intersection. Okay? So, but in Dot we have fewer constants, so we reuse intersection directly because it's already good enough for this. And the client code is also the same. This snippet works in Dot repo. To make it work, we need to add this input, which is not interesting for our purposes. But
Is there any notion of subtyping? Because one thing a refinement type is a subtype of the.
OK, yes. So the Dot model subtyping, because I didn't mention it, but subtyping is a crucial feature. And indeed, the intersection of two types, it's basically the intersection of the sets of values. So as you could expect, it's indeed a subtype. So the intersection of A and B is a subtype of A and a subtype of B. It's in fact the biggest subtype, the biggest type, which is a subtype of both. So it's the greatest lower bound. So this is still using some features which are not in Dot and which we can also encode. So here we have a polymorphic method, listSec. We have no such thing in Dot. However, we have functions. And function can take objects, and object can contain types. So the way we can encode polymorphism is by turning a method into a value, which is a function, which takes type argument containing, which packs it takes an object which packs the type argument, and it returns a sequence it returns the right type. To write this, we need to actually, to write the type argument A, we need to extract it from the value argument that we passed. Okay? So this is still valid Scala code. It's not what you would usually write, but it allows to, it shows that we're using features that we are, other features that are already in dot. We can also express these additional constructs. So it is not something that you would use by hand. Is there a question over there? Or please raise your hand again if yes. So that is not something that you would use yourself directly, but it allows explaining and understanding the additional features. Okay. Okay. Can you take a look at the settings? Are we good again? Yes. So as I was saying, the other thing that we want to change to finish translating this program in dot is by making the recursion that we have in types explicit. So here, we have mutual recursion between the different members of type sec module because some of those use other members. So what we actually write in dot is we had a self variable to bind the current object, and we use it, and the self variable here is called self, and we use it to be able to refer explicitly to the other members of the same value. So the type of isEmpty is a function from the sec member, the same object, to a Boolean. This is not quite syntax that you can write in Scala in all cases. You can write it in sometimes inside traits, but not others. But this is still the internal syntax, which is used in dot and which is used to explain the upper type. Now, I'm a bit short on time already. Not yet. Let me check. So I have other examples of how to use abstract types, but you understand those well enough. The other thing I can show here is how one encodes classes. So we've encoded classes in this previous example just as a structural type containing the members, but classes are additionally nominal types. If you have class foo here, you cannot just create an object which has a member I and expect it to be an instance of foo. So it's the class foo behaves a bit like an abstract subtype of the structural type describing its members. So we don't have them directly in dot, we have them in dot, but we can model them as abstract types. So in type foo factory, we give an interface for a factory of instances of class foo. And we say that a type member foo is a subtype of the class interface, so which has a value member I and potentially other members. And we have a constructor, which will be the only way to construct values of this class. The implementation defines the type member foo to be equal to this type. However, because we upcast this implementation to foo factory, the fact that type member foo is equal to a record containing I is hidden to the whole program except the body of value foo factory. So this body is the only place in the program where we can create instances of this class. So this is how classes can be encoded in dot, at least in simple cases. Using this directly is not enough to model inheritance. There's been work on more complicated encodings, but I will not show them here. So this is the last of the examples I'm going to show. Now we've seen examples of how it is to write programs in just in dot. I'm going to show the actual syntax the actual grammar of dot programs. And it is very small. So here is the grammar of the terms. We have the syntax of values. Values can be variables, or they can be functions, or they can be expressions which create objects. And this expression can contain a list of definitions. And a definition can be a value member or a type member. And inside function bodies, we can have terms, and terms can be values. They can be application of functions, or they can select value member from terms. So this is the syntax of the terms of the dot calculus. And I think it's pretty cool that we can specify the syntax of terms in such a compact way. What I haven't shown here is the syntax of types, and that is a bit more work. The types of dot are much more interesting. So I'm going to explain types by, as I hinted already earlier, by mapping them to set of values. And subtyping, T is a subtype of U if the set of values in T is a subset of the set of values in U. And the types map to set of values, a term is inside, belongs to a type if the term if when it evaluates to a value, that value is in that type. So I'm not going to show how, but this one can use these ideas to actually model, to actually build a semantics and a proof of tightness for the dot calculus, for a variant of the dot calculus. But I'm not going to show that here. Another thing which is important is even if we use this model, we're going to leave out some use which would be valid to enforce abstraction. As in the example we showed earlier, where we showed that abstract types are not equal to their implementation. So here is the grammar of types of the dot calculus. There is a bit more work here, but still relatively small compared to the types of full Scala. We have types for functions. Those are dependent function types, as available in .t. We have records containing a value member. We have records containing a type member. We can intersect those record types to obtain bigger record types with multiple members. We can intersect them using the intersection type. The other important type that we have is the selection of a type member from a path, which can be a value. In Scala, it's just a variable. Or a path can be something like x.a.b. So we allow selecting value members out of paths to create new paths. And out of paths, we can select type members to use the abstract types we have in them. Then we have types any and nothing. Intersection and union. We have singular types, which is the type containing just single value. In dot, we do not have null. So singular types in Scala also contain null, but not in dot. And the last thing that we have are these recursive types, self to T, which allow, these are what we use to allow record members to refer to each other. So the various types have, the semantics of some types are simple to explain because they correspond to simple theoretic concept. So any is a type which contains all values. Nothing is a type which contains no values, just like it's intuitive in Scala. Intersections and unions behave like their theoretic counterparts. As I was saying, when we write a record types with multiple members, this is syntactic sugar that we use over dot to represent intersections of multiple record types. And the other thing which is important about these intersections is that they are real intersections, so they are symmetric, unlike the types, like the compound types that we have in Scala 2, so A with B, where because in those types, B can override definitions in the type B can override definitions in A. That is not possible in dot. You have good intersections. You also have dependent functions. Yes?
What happens if you intersect two types that have members of the same name but different types?
So, good question. So, because of this interpretation, this says the members of T1 and T2 are the members of values which are both in T1 and in T2. So this means that that in your case, where you intersect two types with the same member in different types, like let's say you intersect val A colon T1 and val A colon T2. The intersection will have the same members as val A colon T1 and T2. So, and this also holds for time members, and this will be important in a minute. So next, we have function types, which here are dependent, because we can use the name of an argument to specify we can refer to them in the rest of the type, as we've seen before. And the definitions of their members is.
Sorry, when you said T1 and T2, can you explain that more? I didn't get that. When I got that they become T1 and 2, but what does that mean?
Well, for instance, let's say that you have a type which specifies a record where, what is a good example? But your type specifies that your object must have a member foo with type, what is a good example? Okay, let's not have a good example. Let's have an example. Foo, again, member foo as type A. Now, this is a requirement. We intersect that with a type which requires val foo to have type B. Now, the intersection requires val foo to have a type which is the intersection of A and B. And yes, and now this means we again must combine the requirements. So maybe A and B require to have a member I and a member J, and then, well, foo must have members I and J with the respective types. Okay? That's cool. Yeah.
Are these full-on pi types, or are these path-dependent function types?
These are path-dependent function types. So these are, okay. Scala has path-dependent types and not dependent types, and the reason for this, I don't have an example showing that, is that when you apply a path-dependent function, you can only apply it to a path. So which is something which is already treated as a value. With dependent types, you also have the value you have in types, you can have computation in them. But then you must ensure that this computation is strongly normalized and is totally deterministic, because if you have an expression a path that you use in a type, and it better evaluate always to the same result. So that's something which is crucial for the soundness of the type system. Okay? Now, yes, so we have these path-dependent function types. We, as a special case, we obtain normal function types. We also have singletons. Those are not parts of dot, but of later additions called p dot. There's a paper this year. And this p dot type maps to the set which only contains the result of evaluating p. And as I mentioned before, we have some abstraction here. So if we have a value x of some type A, and we say that y as type x dot type, there's a typo there, we can set y to be equal to x. We can also make another copy, z of x. However, we give it type A. This means we hide the fact that z is in fact a copy of x. That's an implementation detail which we've hidden by upcasting the value. And so as like in Scala, now this fact is hidden, and we do not allow to assign, to use z as a value of type x dot type, because type checker allows us to reason about what we know statically about the program. And the other motivation is, if we hide something by upcasting, it means that we might want to keep that as an implementation detail and change it. So nothing new, but this is the sort of thing that we again must model in dot. So we also have recursive types which allow the types to refer to each other, and I'm going to hurry a bit and show type members. These are the most crucial features modeled in dot. For a type member, we specify the name and we specify the upper bound u and lower bound l. So an inhabitant of this type must actually have such a type member, which must actually be a subtype of u and a supertype of l. And we can use this to encode definitions by setting the two bounds to be equal. In this case, we know that the type member A must be equal to t. Now, as a consequence, one can try to understand, well, if you have a type which requires A to be equal to t, and t is a subtype of u, is this record type A equal t, a subtype of A equal u? Mm-hmm. I mean, indeed, exactly. Or I expect if t and 2 are different, it's not going to be a subtype. Because to have a subtyping relation between two abstract type, between two such types, we need the range. The subtype must specify as a narrower range. So I think this is at some point something that Scala 2 gets wrong, but I don't have an example here. Anyway, here we model this correctly. We also have type selections. If we select the path p.a, what is going to inhabit it are the values which inhabit the actual type which we have in there. So if p.a points to t, the inhabitants, the set of values is going to be the values in t. However, the type checker doesn't always know this fact. It doesn't know the type which is contained. It only knows the type which is specified by the bounds. So what we can say is that if p, this is slightly complicated notation, but this shows what we can deduce in a type checker. I'm not going to explain the full notation, but if path p, we know that it has a type member A between L and U, and then we select p.a, this is going to be a type between the upper bound U and the lower bound A, and the lower bound L. So this is the main typing rule about type members, and this is also what allows us to support definitions. So there, if A is between T and T, then p.a is a subtype and a supertype of T, so it's equal to T. So one thing which, for instance, we see an example here, but since you understand subtype, it's straightforward. If we don't know for a type fix.a is equal to int, but we hide that, we cannot convert just so between a and int. The last thing I want to mention is that values which have an abstract type member, they represent proofs that the lower bound is as a type of the upper bound, and we can use them to implement coercions between those two. So we can use this patterning in code, and this is the main source of complexity of the actual proofs. So because you allow encoding proofs of subtyping and carry them around, you must the soundness proof for dot must show that when you have one of these, when you have such a proof, it's when you have a value with such a type member, it's such a valid proof of subtyping. And this requires ruling out lots of features from Scala 2, selections from lazy vals, from methods or type projections. So this is one of the most or the visible changes arising from dot in Scala 3. That's why I'm going to mention it. I'm going to jump ahead. So we're out of time. So thank you for your attention. And if you remember one thing, is that dot is a small calculus which lets us study some of the core features of the Scala core type system very thoroughly. Thank you very much for your attention.